Thank you so much for watching this online video tutorial. Like, comment, and share, as well as subscribe to our channel at Good Better Best Online Videos for more video content. Okay, welcome grade 12s to the revision session, I think, before most of your mock papers start to take place. Okay, so what we have here is question 6 was one of the requests that came up. It's basically the stoichiometry side of the paper. Although stoichiometry was mostly taught in grade 10 and 11, this is this question where they mix in some stoichiometry questions into the question here. So we're starting with question 6 and we're taking a reversible reaction. So question 6.1 is define the term reversible reaction. So I'm going to leave the reaction there, and unfortunately, just where the place the question is phrased, I can't fit it all in on the question paper. Okay, so we're going to define all the way through, and then we're going to go all the way through here to finish at about 6.7.2. This is not to scare you. This is real life. 28 marks, so it's quite a big section, okay, in this paper. So let's take it from the top. There's the reaction, happens in a closed container. Let's do this and then we'll mark it later. Okay, 12s. Okay, let's just have a little quick squeeze here. 6.1, they define the term reversible reaction. Okay, so we're going to treat this proper mock exam. So obviously you won't write in this color. That's September exam. This was last year's one from the Eastern Cape Education Department. 6.1, the reversible reaction, obviously we know is a reaction in which products can be converted back into reactants. Okay. Didn't write that word the best there, so let me try and fix up some of my wrongs. There we go. Reactants, that is with an A. Yes, there we go. Okay. That was 6.1. Okay, reaction in which products can be converted back into reactants is reversible reactants. Okay, or reversible reaction rather. Okay. Let's go back to the question. Oh, no, sorry. Here's the question. I thought it was open on online. It's not. They give us a graph shows the changes in the amount of a substance, H2, I2, and HI, hydrogen iodide. So hydrogen gas, iodine gas. And you got the amount in the substance in the mole. So from the moment the reactants are pumped into the empty container, we got T0 all the way through to T3. 6.2, which reaction, forward or reverse, has a higher rate of reaction during time interval T0 to T1? Okay, and the answer to that would be the forward reaction. Okay, just write forward reaction. Okay. Sweet. Okay. Obviously reverse is going to go the opposite way. Okay. 6.3, did the chemical reaction stop during the interval T2 to T3? Write only yes or no, or give a reason for your answer. So was this yes or no, boys and girls? Anybody care to explain? Anybody yes or no?
Wait, can you repeat the question?
So, yes or no to question 6.3. Did the chemical reaction stop during time intervals T2 to T3?
Yes. No.
Okay, so there's a conflict of answers there. Do you guys want to debate that out? One said yes and one said no. Who's more right? Let's look at that question again. Did the chemical reaction stop? In other words, there was no reaction, no more reaction taking place between T2 to T3. Let's hear those answers again. What say Abdurrahman?
I'm still saying no.
Okay, what says you, Mr. Ravens?
I mean, it reached equilibrium.
Ooh, okay, hold on. I like that. Okay, Mr. Ravens, I'm gonna let you hang on that one, okay? And I'm gonna bring it into context for you.
Pardon?
It did. So we can clearly see that between time intervals T2 and T3, that the rate of the forward reaction, I was going to say forward reaction, okay, is equal to the rate of the reverse reaction. Okay, which means the reaction has reached equilibrium. Okay, so if the reaction has reached equilibrium, that does not mean that the reaction has stopped. Hence, no, it has not stopped. It's just reached an equilibrium point where the rate of the forward reaction is equal to the rate of the reverse. But no, it has not stopped. Okay, it definitely looks like it has stopped after T3. So at T3, like this point here. So not between. This little point here, between T2 and T3, no, it hasn't stopped. But definitely from T3 onwards, nothing left. That's when we know it's stopped. Pretty cool. Awesome. At time interval 3, so at T3, the pressure on the equilibrium system is increased by decreasing the volume at constant temperature. 6.4 says, now how will the increase in pressure affect the following? Write down increase, decreases, or remains the same. For 6.4.1, how will the increase in pressure as a result of decreasing the volume, how would that affect the rate of the reaction? Answers, please. I mean, I asked nicely, guys, please. For 6.4.1, how is that going to affect the rate of the reaction? Ah, okay. See, someone answered silently in the chat. Eluded my eyes there for a second. But yes, the answer for 6.4.1 is it will increase. Let's start on a new page for the entire question 6 and let's write a more decent color. 4.1 increase. Okay, smaller surface area, smaller container. The pressure is now increased. I think that was the question. Yes, the pressure's increased, so we've got increased pressure. Rate of reaction will obviously increase now. 6.4.2, the number of moles of the product, hydrogen iodide. Will that increase, decrease, or remain the same? Anybody? What say we on 6.4.2? 6.4.2 indeed remains the same. So 6.4.2, the number of moles will not change. Okay, so number of moles of the product that is formed will remain the same. Okay, things that can affect the mole is, of course, your concentration, of course, the mass of the reactants, of course, or the mass of the product, the molar mass, etc., etc. Those things affect the mole. 6.4.3, I believe, was the concentration of hydrogen iodide. The concentration of hydrogen iodide, 6.4.3. How will the increase in pressure affect the concentration of hydrogen iodide? Anybody? Watching the chat box very closely to see any answers. Increase, decrease, or remain the same. Increase is correct. Thank you, Zuleika, for answering all three of these questions. Increase, it is correct. Okay, all of them will increase. Well, not all of them increase. The concentration of hydrogen iodide will increase. Okay. Let's rock on to 6.5. Now, 6.5 asked you to explain why the hydrogen iodide increases. Alright? So, the reason why, and I think I'll take this one. Let's write in red. Okay. First of all, the amount of the substance, which is the mole, right? The amount of hydrogen iodide, that obviously remains the same. So I think that was 6.4.2. Let me just check. What was that? Yes, number of moles. So there we go. So the amount remains the same. Okay. But the volume decreases. Okay, the volume obviously decreases, which they mentioned at the start. Okay, so now the volume decreases. If the volume decreases, the concentration now increases. The concentration now increases according to what? The formula. According to C equals N over V. If your denominator goes down, of course you'll have a bigger answer to the fraction. Okay? Makes sense. So, if this goes down, this goes up. Okay. The inverse proportionals. Okay, coming into play here for this one. Okay, so that was our answer for 6.5. Okay, any questions on that, guys? Any questions? Alright, for 6.6, they say the table shows the equilibrium constants, Kc values, for the reaction at different temperatures. So temperature at 448 degrees, equilibrium constant there at 50.3, a little blank one there, and then 227 degrees Celsius, we got a higher Kc value. Okay, equilibrium constant. Now 6.6.1 asked, is there a high or low yield at 227 degrees Celsius? Please give a reason for your answer. So what was the answer there? Was it a low yield or was it a high yield? High, indeed it was. Okay, it was definitely a high yield. So that's what we'd obviously include there. So it was a high. Ooh. Sorry about that little noise. My little container thing just decided to drop out of my hands. It's definitely a high yield. Okay, reason why? Because our Kc value is large. Okay, it's quite a large one. Okay, we can't say Kc is greater than 1 because at 448 degrees Celsius it was also larger than 1. Okay, so Kc is quite large, and it's definitely larger at a lower temperature than what it is at a higher temperature. Okay, 6.6.2. Yeah, I think the reaction is the forward reaction exothermic or endothermic, explained by referring to Le Chatelier's principle. While it is definitely exothermic, and according to Le Chatelier's, okay, is that the value of the Kc value, decreases. The value of Kc, equilibrium constant, decreases with an increase in temperature. Okay, it definitely decreases with an increase in temperature. But as temperature increases, so I'm just going to shorten temperature to temp. As temp increases, the products decreases. Okay? In other words, the Chatelier's principle says that the reverse reaction is favored, okay, by an increase in temperature and not the forward. Okay, the reverse reaction is now favored by increase in temperature. Okay, another way to maybe say that is because the value of Kc increases with a decrease in temperature. So we should say the opposite of this now. Okay, the value of Kc increases with a decrease in temperature. As temperature decreases, the products increase. Okay, therefore the forward reaction is favored by a decrease in temperature. Now we know that outside of Le Chatelier's principle, usually the forward reaction would be favored by an increase in temperature. With Le Chatelier's principle, it's different because we're not just looking at rates of reaction alone, we're looking at the equilibrium constant. I think 6.7 was calculate the concentration of hydrogen iodide at equilibrium. But let's just first read this little bit here. The reaction is started by placing hydrogen gas and iodine gas into an empty 0.5 decimeter cubed container, which is then sealed and heated. When the reaction reaches equilibrium at 448 degrees Celsius, it is found that the concentration of hydrogen and iodine are 0.46 mole per decimeter cubed and 0.39 mole per decimeter cubed, respectively. The value of the equilibrium constant is equal to 50.3 at 448 degrees Celsius. So they wanted us to work with the first line. Calculate the concentration of hydrogen iodide at equilibrium. Okay, well, first things we got to say, well, Kc is equal to the products, which is Hi, concentration of the products, divided by the concentration of the reactants. Okay, so we know that the Kc value was, let's write it a little closer here, 50.3, and that was equal to the concentration which we are uncertain of at the moment. But we do know that hydrogen was 0.46 and iodine was 0.39 respectively. So we multiply both sides by this little product here, and therefore the concentration of hydrogen iodide is going to be equal to the equilibrium constant, which is 50.3, multiplied by 0.46 times 0.39. Let me just check my reaction again. Oh yes, I forgot that little the balancing number 2 there. Okay, that was my problem here. We've got a little squared there, so we've got to take this little squared away, therefore away there, sorry, and add a squared here. So we'll get something by 9,02382. That's the entire decimal stops there. So we obviously got to square root this number. Okay, and therefore the concentration of hydrogen iodide, will now be equal to, that should be just 3,003, so that's basically just the whole number 3, so 3 mole per decimeter cubed, and that was 4 marks. Alright, now the big question here was now calculate the percentage yield, okay, of, I guess, also hydrogen iodide, which is at 448 degrees Celsius. Okay, 7 marks. Okay, let's see if I can do this the best that I can. Okay, let's come all the way to the top. Okay, I think that pretty much is the top. So we're going to have to first use a calculation that's looking at the mole. Okay. I'm gonna have to look at the mole first. Okay, so obviously we performed that little table, which I'm going to just construct as quickly as possible without taking up too much time. This is going to take most of the space on this little page though. Do apologize for that. Okay, cool. So okay, just mix it up like that. So let me see, we got 3, so I need, okay, that's 1, and I need to also halve this up as well. Okay, so let's use maybe some other colors. So this is H2, I2, and that's HI, or with a 2 in front of it, 2HI. Okay, so I've got initial mole, I've got change in moles, I've got mole equilibrium, and then the concentration, which is at equilibrium. Okay. Okay, so let's see what else that they gave me. Okay, let's see what else they gave me here. So they gave me the concentrations of, I've got actually the concentrations of them all. Actually, I've actually got the concentrations here of 0.46 was for hydrogen, 0.39 was for iodine, and I calculated it. It's 6.7.1. The hydrogen of the concentration of the products should be 2b3, and now surely I can obviously figure out that the initial moles was 0 at the beginning, and I should be able to work out now. This was the concentration. So if this was the concentration here, then the moles at equilibrium should be, if I want to calculate it, should be N is equal to C times V. So the concentration was, let me see, 3 times 0.5. So that means, therefore, the amount of moles is 1.5 moles. And that should also be 1.5 moles there too. Okay, so that's pretty interesting, I think. Okay, so let me just try and work out these 2 moles at equilibrium. Okay, so these is, I obviously took the same ones and calculated using the same formula here to get the number of moles at equilibrium. So the change in moles, if I've got 1.5 moles here, which is the same as my equilibrium moles, I can use my mole ratio to obviously figure out what these 2 numbers are going to be. So this is the mole ratio of 2:1:1, so half of this is obviously 0.75, and that's 0.75, so just used my ratio. And of course, I think it's the difference or the addition of it. Let me see, 1.95 plus 0.75. Yes, so it's these 2 plus each other that's going to give us what was our initial mole. So that's 0.945, and that should be 0.98. Okay, because usually the change in moles, if you take the difference, you'd get the moles at equilibrium. Okay, so you work backwards now. Okay, and that's our table filled out. So we've got to check what is the limiting reagent here, the substance that gets used up first. So 0.945, which is basically 0.95, that's basically 0.980. So the limiting reagent, the one that gets used up first, of course. Okay, so that works out perfectly. Our table's filled out. So what I'm saying here, okay, is that the amount of moles theoretically that should be produced as a result in the ratio of 2:1:1, right? Because iodine is our limiting reagent as it has the smallest amount of moles. That's going to get used up first. So obviously I can't write here, guys, so I'm just going to say the number of moles of hydrogen iodide that are theoretical that should be produced. At the moment, I only got 1.5 at equilibrium. They're the same. But theoretically, because it's a limiting reagent, they should be equal to 2 times the number of moles of iodine, which should equal 2 times 0.945, which should give me 1,89 moles. Okay, so theoretically that should be my moles for hydrogen iodide. That should be my moles. However, that's not the case. Okay, I only got 1.5. So I take my formula and I say percentage yield must equal to the number of moles that I was actually produced, so in other words actual, divided by the number of moles that were obviously theoretical. Okay, in this case it's going, sorry, my elbow keeps knocking the volume button. Actual, I got 1.5. Theoretically I should have gotten 1,89, and we've got to times that both by 100, and therefore my percentage yield is equal to about 1.5 divided by 1,89 times 100, 79.37%. Thank you so much, grade 12s, for joining me on this little revision of question 7, which is stoichiometry. As we saw, it was a big question, but you all championed it and did very well. Hope you all enjoyed this tutorial video, and I'll catch you in the next one for some more revision ahead of the September and final exam. Sorry for this little computer ad that has popped up here. Anyway, I wish you guys all the best for those, and don't forget to like this video as well as to subscribe to our channel. Good, better, best online videos, those that are watching, and hope you enjoyed the tutorial, and I'll catch you in the next one.